This is the second video on redox reactions. This is on a technique called half reactions. Now, from the first video, you should recall that oxidation reduction must occur at the same time. If something is reduced, something must be oxidized. But as stated in the same video, you can conceptually think of two separate reactions occurring, then being combined, the reduction reaction and the oxidation reaction. Each of these reactions are called half reactions. Now, a half reaction will include free electrons. So let's look at this example of zinc and copper ion reacting to form zinc ion and copper ion. Something has to be reduced, something has to be oxidized. The reduction, gain of electrons is reduction, occurs with the copper because the copper ion gains 2 electrons to become the copper metal. That means the zinc must be oxidized. Zinc becomes zinc ion plus 2 electrons. If you have half reactions, you can figure out the overall net reaction. And when you are given half reactions, by convention, the half reaction will be in the reduction half reaction form. So in a question, you'll be given something that looks like this. In this case, copper and nickel, both in reduction form. You'll also be given something called the reduction potential, which has a unit of volts. These are the reduction potentials for the copper and nickel, respectively. Now, the reduction potential for any half reaction is determined experimentally, and it will either have a positive or a negative value. From this data, I can tell you that this is the net equation. But how did I know that? Well, to go from the half reaction to the net reaction, you need to figure out which half reaction will stay in the reduction form, and that's the half reaction with the more positive reaction potential. The other half reaction gets flipped. Now you're going to balance the electrons because now the reduction should have electrons on the left side of the arrow, and the oxidation has electrons on the right side of the arrow, and you want to get rid of them. You're going to add the two half reactions together, because two halves make a whole, and your final check is to be sure that the atoms and the charges are balanced. So here is an example. We're going to be looking at silver ion and iron ion as the half reactions. We see for the silver, the reduction potential is positive 0.80 volts. For the iron, it's minus 0.44 volts. So we need to determine which half reaction will remain as reduction, and that's the half reaction with the more positive reaction potential. So here, the silver is more positive than the iron, so it will remain in reduction form. Therefore, the iron must be the oxidation half reaction, and so it has to be flipped. Now we're going to balance the electrons as needed, and we see we have 1 electron here and 2 electrons here. So I'm going to multiply the reduction side by 2, which means I have to multiply everything by 2, and so now we end up with something that looks like this. Now we're going to add the two half reactions together. You can see I have 2 electrons to the left of the arrow, 2 electrons to the right of the arrow. So when the two half reactions are added up, these two will cancel out. The final reaction should not have any electrons in it, and it looks like this. So now I'm going to check the atoms and the charges. I have 2 silvers. I have 1 iron. 2 times 1 plus is the same as 1 times 2 plus. So that checks out. So here is one for you to do. Stop, get the complete reaction, come back, check your answer, then I'll walk you through it. Go. And this is the correct answer. How do we get that answer? We follow the steps. Got to figure out which half reaction will remain as reduction. So we pick the more positive reaction potential. Though both reduction potentials are negative, the 0.44 is more positive than the 1.66, so iron stays in the reduction form. That means aluminum is the oxidative form, and so it needs to be flipped. Now we need to balance the electrons by multiplying the entire reaction by whole numbers as needed. We have 2 over here, we have 3 over here, but that means there's a common multiple of 6. So I'm going to multiply this by 3, and this side by 2. So it's going to look like this. Now I'm going to add the two half reactions together, and once again you note that these 6 electrons cancel out these 6 electrons, and you get something that looks like this. Now we just need to check the atoms. 3 iron, 3 iron, 2 aluminum, 2 aluminum. 3 times 2 is the same thing as 2 times 3. This is balanced properly. So this is the correct overall reaction. So to review half reactions, you can break redox reactions into 2 half reactions. If you're given half reactions, you can figure out the net equation. You'll almost always be given the half reaction as reduction half reactions. Half reactions always will include free electrons and will have a reduction potential. From all this data, you're going to need to figure out which half reaction needs to be rewritten as the oxidation reaction. And when you do add the half reactions together, the electrons must cancel out. So you're going to follow the steps. To determine which half reaction remains as reduction, it's the one with the more positive reaction potential. You're going to flip the other equation. You're going to make sure that you balance the electrons, multiplying the entire half reaction by whole numbers as needed. You add the 2 half reactions together. The electrons better cancel out. And then make sure that the atoms and the charges are balanced. And that completes our introduction to redox reactions. Further down the line, we're going to come back to these and begin to utilize half reactions to determine how voltaic cells or batteries work.